he's gonna start off, and then we're gonna do presentations. Mine's the second to last, and they're each gonna be about 30 minutes long.
Okay.
So I was talking about me coming to one of you guys like band sessions.
Oh, okay. Very nice. Yeah, it'll be fun.
Yeah.
It's loud.
Fun.
Yeah.
Cool. Good. Excited?
And if you want to sit like a nicer chair, if you don't want to sit.
Did you share your presentations with her? Yeah.
What are all of yours called?
All right. Yeah. Just great.
Mine's right
All
at
right.
the
Good
top.
luck.
I'm Stephen Burkhardt, UDD something. Mine's the second one.
I put mine in the shared drive. I said it. I feel like it should be.
I think you can put a shared drive.
Shouldn't everybody?
Yeah, it's in that.
And then Matthew, what's and Tim, what are yours called? Guys,
Mine's in the.
like it's not capitalized. Here, do you want to say
Or did you just push it out?
No, I just don't. We're in the other quarter.
I just wanted to
Did you saw that?
And then Tim will be Tim.
Yeah, that's definitely
Tim, what's your presentation under?
Tim Larson, DVD, or final DVD presentation. Tim Larson, final DVD.
I don't see it. No, it's this one.
Yeah, that was nice. Shout out from one of the people that never took any of my classes too.
Ryan Calvin.
Ryan.
Oh yeah, they're a lot of people talk about it now.
Well, too late for the
Alright, EDD students, I have an extra tab here, so all you need is switch right to it, and you can just check and you're good to go. So that way it'll just smooth up the process for everyone. Can I just put some percent?
Yeah, you can leave it up there. I think we got it. We're looking at that clock, we got 1 or 2 minutes. Hello, everyone. We're going to start right at Okay, the YouTube video is live. For those of you that haven't seen me in a while because you haven't been able to come into school, I'm Matt Slauson. I'm the instructor, teacher for this class, which is Engineering Design and Development. Excuse me. The idea behind this class is that it is a capstone course for all of the engineering classes that we teach at the school. So most of these students have taken at least 3, and some of them have taken 5 of the engineering classes. So they start off with IED, which is Introduction to Engineering Design, which is a drawing and designing, computer integrated manufacturing. This is really hard to breathe when you're a little bit nervous. Computer integrated manufacturing, a lot of these students learn to make instruments and use tools and machines. digital electronics, so they learn to do circuitry and program. Principles of engineering, where they learn things like basic engineering concepts like stress and strain and mechanics, a little bit of electronics, so kind of a survey course of a little bit of everything. So the idea behind this is to get students to solve a problem of some sort that they identify and use the skills that they learned in other classes to solve the problem. Something hopefully that they buy into, something that is interesting to them, something that excites them about engineering. So that's the general concept. To implement that, the first half of the year, which was a struggle with the COVID thing, we did a design project using the concept of the COVID and sanitation, and they designed and built a hand sanitizer dispenser that you didn't have to touch, right? Nobody wants to touch a gross little device to clean their hands. So, and that came out really well. They did that as a team. The capstone project that they're doing has been going on since about mid-year till now. And then this is the presentation for this. So the format of this is every student gets approximately a half an hour, 20 minutes to present, 10 minutes to answer any questions you may have. I will let them decide whether or not they want you to ask questions during what they're doing or ask questions then, and they can tell you that. It's their presentation. So I encourage you to ask tough questions. It's going to be tough to see from way back there. If you want to move up a little bit, you're welcome to. What else am I forgetting to tell you? Unfortunately, we're still under the mask mandate inside the school, so we got to go with that. And the order will be, let's see, Hope, Ben, Tim, LB, Jacob, and Matthew. Okay, so without further ado, Hope, you're up. Hope, can I stop you just for a second? Because I'm probably one of the older people in here. You got to project a little bit more. It's kind of hard to hear with the mask. Thank you.
All right, hello everyone again. I'm Hope. I'm an engineering student. My research is basically focused on the idea of ergonomics, which is really dealing with more of a human-centered idea of human factors, which I will get into a little bit. I'd like to thank expert Dr. Perez and Dr. Malachowski for their work and their research as well. All right, so first I just want to get into the idea of ergonomics and also anthropometry, because they are the two factors that are really going to be driving this entirety of this process that I've been working on. I also would like to mention a few of the interdisciplines that you can really get involved in. So for example, you can go anywhere in the STEM field from energy, defense, and healthcare, all the way to kinesiology, physiotherapy, and psychology. So it's really interdisciplinary, allows you to cover a lot of fields. Now the idea of anthropometry in relation to ergonomics is the idea of the user space. And this really focuses on studying and measuring the portions of the human body, but also how that relates to the comfort of one's environment. And yes, there is both a lot of quantitative and qualitative factors that go into this. So moving on with ergonomics, one thing I just like to show is a resource from Dr. Perez via Berkeley. So this was measurements of the human body. So as we're noticing, everything goes into many different facets. So what I'm saying by that is the fact that we're noticing how aspects such as the head to legs and the core all have an aspect in how the user design is included. Okay, so moving on to my design brief, my idea was to allow ergonomic position and also working to maintain the productivity of the user without causing pain or discomfort. Because a problem that I've noticed is something dealing with the idea of pain and discomfort that is caused from poor position. And this is also known as something dealing with video mobility, as also dealing with the idea of changes in posture, also causing changes in So my statement is really focusing on the idea for an integrative aspect. So this is focusing on the idea of Stanislaus High School, really students, faculty, anyone using computers in the desk space. Another aspect is the result of COVID. We're going to be seeing more people using a workspace such as home. So the idea of having good posture is really important because you are also going to be spending more time at the screen. So the idea of sitting comfortably and correctly in a consistent manner. It can be a constant hassle requiring constant manipulation of the body and the desk, and therefore hindered productivity. So some criteria includes finding a standard computer size. So this would be dealing with 13 inches for a laptop. So this is what I'm really focusing on, is between the laptop and the tablet, which would also be around 9 inches. And then in terms of another type of computer, which we can think about monitors, my design is not necessarily focusing on that. It's more of a standard desk feature, which is not going to be included in this aspect of the design. Other constraints include the remote accommodating feature, since we were online for a big portion of the year, as well as having this remote aspect integrated with an in-person aspect. Also including different weight adjustments and development time, as we do have time limits and also deadlines as well. So again, like I was saying before, our clients really focusing on faculty, working, and also thinking about human relations, since they would be spending a majority of their time working with customers either via the phone or in office environments. And then for our target consumers, it would be the same idea. So I just wanted to put this, you can really ignore the writing for now, but if we're looking at the breakdown of this idea of the Gantt chart was a way we were able to take our ideas and kind of put them in a way that would be time-ordered instruction. So we're thinking about this, we're also thinking about everything from conception, so the problem and research, to the ideas, the sketching, and also finding interviews, so we can have expert opinions and therefore have a constant way for us to modify our design. This also includes presentation and then micro aspects that I included, such as testing, adjustments, run-throughs, and feedback. And then again, you can see how the colors change over time, so once everything is completed, it can all just be a way to report the progress. Another aspect is a work breakdown structure, also known as WBS. This is a factor that is used in a variety of office environments as well as the professional workforce. This is just a way to organize your sections. So I really chose 4 main aspects, and then I broke those down. So from project development to average and final prep, and then each category has an aspect you can code. So some current solutions that I researched included the idea of the keyboard as well as the feasibility of different types of woodworking techniques. So if we're noticing in the far corner on the right, those are different types of collapsibility features, as well as another feature which is known as a living hinge, as noticed on the lower middle portion right here. These are aspects that I considered with multiple iterations, and it was also a feature that I was able to include and learn from in terms of the feasibility. So some other aspects, again, you can ignore the writing, but mainly looking at the design features here is the idea of a way to collapse and expand, as I wanted to make sure I'm paying attention to the footprint of the design. As noticed in this final design here, we can see that it's not taking up the entirety of the space, but it is enough for a room if you did have a desk. And some other aspects I was considering are ways it can be built together, so including some ideas of different hinge types which need to be spec. Some other ideas included in the research phase included comparing different types of alloys, such as steel, so we have stainless steel as aluminum die cast, as well as some others that I'll be mentioning soon. And then some different types of joint features, as mentioned above. There's also inverted hinge, socket, and pivot, which are considered. And then another aspect here is idea of woodworking again. So ultimately, in my final design, I did end up going with some aspects that include dovetail, but those again can depend on the iteration stage of this working on. So again, more with the design process. These were some initial iterations, some final iterations. So here it's more used in a drawing platform, a tablet to work on different iterations. This is a great way for me to be able to get out my ideas, as I found it was the most good way for me to be able to work on my design. And on the top right was an image of my final designs here on its collapse stage. So I was able to use the standard to get everything on an even footing for one side, and that was able to help increase the size. So other diagnostic solutions that were researched also include the breakdown of metals as noticed above, but what I really liked about this, again, before the writing, is just the breakdown, which is really a great way for research to be done, also in an effective manner. So for example, having different types of metals, having the different types of characteristics, positives, negatives, and common uses is a great way to organize work and research and also figure out which way is a possible option to use. Again, I will also come back to this just for the use of comparing in the final design if any of you have questions regarding cost analysis. So another aspect is identifying SWOT analysis, which goes over the strengths, weaknesses, opportunities, and threats. These also include competition. I compared 3 larger companies just because of their reputation and standing, so Wayfair, Scale, and Paxton. Now, most of them were really geared towards audiences of both your economic status, but also ones that are more budget friendly. And from that, it's able to kind of see where my design would fall in and where I could figure out the niche that I could cater to. Another aspect here, again, the writing basically breaks down how I was able to figure that out, looking at specific features. So, for example, isolated designs, dual monitors, or customizability, as well as lower desk footprint, and also sustainability certificates. In this case scenario, my lab work was restricted to materials in our engineering lab, often can be recycled, and also used. So more of the fabrication process, this is more in my final design. I included thinner, I used 2 different parts. So as you notice in the final design here, on the upper portion was where I would be having the laptop and the monitor to maintain an ergonomic position. And the lower portion, I would also have a keyboard, which would be a standalone, and in this way, the user would be able to maintain a more ergonomic position. Then on the top left, I also used a level to make sure that everything would retain at the same speed. And here is another image explaining the detail of side in terms of position on the desk. So some other possible solutions which were done in the process included some ways of using webbing to curve wood, and in this way I made incisions using a saw, and in this way I was able to add an aspect that ended up being less practical than originally initiated. But during this process, I broke it up into several sections, and in this way the wood was able to bend. And this also includes a model that I in a CAD software. And for some more ideation, I also use clamps to be able to hold this together and therefore be able to reinforce the idea. And then here is some other aspects of iteration. So this was again going with my second iteration, although the reason for this infeasibility was due to the amount of materials that were present. So what I mean by that is that it ended up being more a chunky design, as in it was taking up more of a footprint. Also in terms of time, it was not something that was necessarily feasible. There were many parts involved and therefore would hinder the overall productivity of the user, going back to my design criteria. However, the idea of a vertical adjusting system, as noticed on the bottom right, was something that I continued to evolve with my design leading up to the final iteration. And then here again, I also had some ideas of having a curved aspect that reached out the component out, although that was not used. And then some other aspects also included that with other compartments, possibly for storage. And then the same idea for a second iteration. So for more research, on top of competitive design analysis and materials, were reports and articles reviewed on anthropometric data. So again, just maybe looking at the image here, we can notice this point is seated because I also wanted to include an aspect for both standing and sitting with my design. And although my testing data was only mainly to record people standing, it is still an aspect I would like to consider in my design. But here we can notice there are specific distances and angles that are included with the best posture and the overall tilting levels that you achieve from having the correct position. This includes not only the desk, but also the chair and the height of it. So a lot of factors go into this, including measurements. And then for the right side, these are some other aspects of designs. And you can also notice the woman on the right-hand side is what's considered a neutral posture when sitting. Again, these are more design ideas that I had or researched for that matter in terms of finding ideas and also for current analysis. So some specifications I did because, again, as I was saying, the types of materials and also of devices that I'll be using ranged from tablets and also computers. And then in terms of that, I researched different types of weights and models. Now, what I was using, I was basing on my own devices that I have, so currently I do use Apple devices, but it does not matter which company you use because overall, the average dimensions would be between 13 inches for the computers and then for the tablets around 10 inches, and that's pretty pentagonal. And that is a pretty standard range that also works for the range between 5 and 95% of users that are using this. Another aspect to consider is the idea of humidity and temperature, as these usually have a temperature range between 32 to 85 degrees Fahrenheit, and then anything below or above that will hinder the aspect. And then we also have to think about the materials itself, so using birch in terms of that and humidity. And then again, these on the right side, we're just explaining some of the size and weight breakdowns. So for the solution iteration process, what I include were the last two designs that I analyzed. So on the far right, you can notice a picture of what seems to be a more structurally sound and professionally designed one on the top right. That was in a room of one of our faculty members here, and I used that for competitive analysis. And then on the bottom right is where I used a dovetail method to insert a curved slot that would allow for a more collapsible or retractable idea. However, this was not useful in the end because of the inability for the device to maintain a balance. And on the right here is part of the second part of my design, as noticed with the legs. These are able to use a hinge underneath to work completely 180 degrees, and therefore be able to adjust to a collapsible aspect. And this also helps with the user in the sitting position, as sitting you would be adjusting quite a distance vertically, so therefore you'd be able to use both designs. Another aspect here was the types of materials I was using, so I would be measuring from a table saw and then I would be cutting in. Again, these were from earlier designs, but it's important to notice the variability of the variations in process as with the engineering process. Other aspects of prototyping, I took a part of a monitor of a computer and was able to see the aspects of how the adjustment tracking system was used. What the aspects of here that I couldn't necessarily use, which is the spring system and the ball bearing system, and also aspects that were cement, so I could not take it apart any further, but it's still an important aspect to be able to consider. And here again are more iterations of prior designs that are more close-up, so it's easier to see. And then for the creation of the solution, well, this was based on some technical needs. So research outlined in anthropometric sources were done with the current body measurements. So I used data on actually from the Center of Disease Control and Prevention. They have studies done every 5 years as well as every year, and those were used to compare adults and teenagers, specifically with our range, focusing on anthropometric measurements from knees, the height of the head to the ground, and also different positions when sitting and standing. So I determined that 25 inches would be a base length for the criteria of users, and then 10 inches from the base height, and then the adjustment of 6 inches in a vertical tracking system, and the 90-degree extension. 90 degree can also be reached to 120 degrees depending on whether you're standing or sitting, and also the height as well. And then fabrication techniques, I kind of included this from a variety of solutions that were possible. So heat wetting was for prior solutions, but the other, as well as the quarter sections, but using the miter saw, this steel folding machine, CAD, and also soldering was used as well. So then for the setup and tear down, just because of time, I'm just going to show a quick video here. I'm just going to do this and put this on. So here, you can take it down. You just have to remove all of your devices. Then you just have to screw on either side, rotating, and then you can adjust vertically upward. And then once you do that, you're able to just secure back in place. And then doing that will ensure that your devices will not slip. And then for that, you can also put your keyboard on both your at the bottom end, and then here you can adjust that if you were going to be sitting down. So if you notice the bottom section, that would be for having the second design criteria, which is to be able to adjust for both sections. And then, okay, so for testing, all of this was broken down into two sections. So I was able to take the height of users. This is not in descending order. This is done based on the number of trials. So of course, every student has a different height, and that is negotiable. You cannot change the height of the person. But doing that was important to consider based on the angles I was using. Then using a protractor device, such as this one was created, I was able to measure the length of arm, and using that degree, I was able to determine whether or not they were at a ergonomic position. From my data, I recorded that we had quite a variability in differences, including whether the user was at a lower height or a higher height. And using this, I also calculated that my percent error was rather high, from 120 degrees, as well as for 90 degrees, which is a significant difference, which proves that it is ergonomic, so I would not necessarily be meeting the criteria. Now, for general conclusions, I also noticed the influence in data collection and universal design, which is the idea that source of error, which we'll get into in a second. And then universal design is that when I was creating this test, there wasn't necessarily a one script that I had. It was the same for every single person, which also meant differences in how people are perceiving the test can have an impact on how they're understanding it and therefore influencing it. As well as there was a more manual assembly than initially anticipated. So for example, while there are knobs to adjust, you still have to hold the top in order to adjust the test. And then for issues with the neck and the screen, there was user position, which would also affect their ability to have an ergonomic position. And therefore, because I cannot influence the design, I cannot tell them at the beginning whether or not they are in an ergonomic position, as it is what's most comfortable for them. And then sources of error also include the inaccuracy of measurement. So for example, paying attention to which part of the arm that I was measuring from in the exact order every single time, as well as the consistent set of criteria they mentioned, the measurement of extension, and then the data that was derived from that. As well as paying attention to the criteria and how collapsibility could sacrifice the user experience and adjustability in terms of being able to meet both cases. Ways to improve this would be possible on the survey of intuitive design, user experience, and refinement dimension. And mainly the intuitive design is the idea of having a universal design, something where the user can automatically come up to it and understand how it works without being instructed, as I have to do with this. So with some expert notes with the industrial hygiene income factors, I interviewed Dr. Valerie Perez and Dr. Roman Malkowski, both are industrial hygienists who work currently at the University of Pennsylvania. Some main aspects that were discussed include areas of study that one can go into with ergonomics, including chemistry, also occupational health, and then ergonomic fit with user compatibility, as there are many factors that are involved. And then with human factors and aspects to the environment, there are differences in how the user can interact and also comprehend their environment. And then in terms of UPenn work in ergonomics, one aspect that I want to consider is they were able to inform me about how projects that they've worked on, such as a student who was disabled and therefore noticed that around campus there were a lack of abilities for ergonomic design for them to reach certain things. So using that, they took a camera with the user who moved around throughout the campus and able to take pictures and record areas that were difficult. And from there, they were able to figure out aspects that can improve in the workplace and also the accessibility for people. Another aspect is taking a survey of users, figuring out which chairs can be involved, such as when picking out new equipment. One aspect that happens a lot is the ideally looking more as aesthetics rather than the functionality. And so one thing they take into consideration is taking surveys for users where they test out different types of chairs or whatever device that would be being used for the classrooms, and then whichever one gets the best response is the one that they will end up using. And then another aspect for offices is a lot of factors involving the light and the amount of time that you're going to be working at. So different occupations, for example, will have more or less time involved in sitting and therefore have different aspects in the type of desk that you'll be using. And then in terms of decision making, what goes into that is a lot, including the type of person, how long one can stay at a workplace. And then the effects on general population would be concerning how one can be able to use this efficiently with different types of people and therefore consider it to be inclusive design. And then some feedback that I got, again, was mostly focusing on looking at the purpose, of course, before looking at the aesthetic. Also making sure neutral postures are considered, especially from moving from sitting to standing. And then for the desk space, again, looking more eye level and then using an external mouse placed close to body, and then also paying attention to when wrists are changing. And then other fixes, you can use boxes of footrests, you can resume settings with monitors. These are more things that can be done manually and don't necessarily would need a device for. And then in terms of other testing, I took people from multiple heights and then instructed them how to use, and then mainly focusing on the 90-120 angles. And then again, for desk surfaces, this is keeping the idea of making things that could be happening. So for example, keeping your knees within the same position, keeping your feet parallel, ideally flat to the floor, and then also keeping a flat surface, making sure that you are at position. And then in terms of movement and productivity, this would be more like 2-hour sitting periods, but you could take a break such as scheduling lunches. And then in terms of noise, finding either ambient noise or noise canceling headphones that would help you focus, paying attention to overhead lighting and then screen tilted away. And then with remote work, things that you can consider if you do not already have a device would be using books to raise your monitor or virtual training. And then home offices can be non-stressful, which is why it's important to consider what other devices you can use. And then with university work, it can be difficult. This is just something that is both important me with canceling because all of us are different and also have different functions. And then there can also be different types of heights and just material. And in terms of the cost of production for this one, because of the types of materials that were used, it was rather expensive, which can also depend on the price range. Now, when we're thinking about doing industrial aspect with large-scale factors, the idea of buying from bulk can also change. And then in terms of the weight, this would be under 10 pounds, but this device is also something that would not be moved around quite too often. So once you put it in, it's keep it there to the majority of time. And then for estimated cost of mass market, this would be something concerning mainly 10 to 25%, so 100 to 110 to 125. And then for the viability of weight in a personal commercial space, it would be relatively larger than form, but again, this can be changed with different types of alloys, material, steel, as well as the bulk version. Right, are there any questions? Yes?
At the beginning, when you were talking about why you chose this project, did you intend for this device to solve a problem that existing devices don't?
Yes, and so this, because ergonomics is also a very saturated market, there are also many that already exist currently. One thing that I did want to pay attention to is the fact that I also use both a laptop and a tablet, so I was also considering looking at a way that I would integrate with the design, so being able to use both on the same platform, because a lot of them was either one or the other, you wouldn't be able to use both, and so that's why I put it here. I do not have my tablet with me. This is an aspect that I still include included, they have us in between, I would include the aspect.
Did you at any point in time consider attaching it to the table? Because most of the ones I've seen attached, or they stay.
Like having an attachment just like as, instead of like another device on top of the table.
The ones that I'm familiar with actually attach to a table so that they don't move at all.
Right, yeah. So this was not something that I necessarily prioritized in my design just because I thought the idea of having something that would allow you to just at your own rate. But yes, that could be considered for a possible solution.
Because it's going to move, and then it's not going to be right.
Right, move as in saying the entire design or just, yes.
If it's mobile on the table, it will move away from the ergonomic position, which I think is why the ones I've seen now are fixed, so that they stay tailored to the specific user.
Right.
That adds a whole other device.
Mm-hmm. Yeah, so for that, the aspect of, because of the types of material that would be used, it would not really move too much as often unless someone is physically moving the desk in a different position. In that case, you wouldn't necessarily be adjusting your entire desk all the time. So for that reason, that's why I consider that it would be still a feasible option. But yes, it could also be, what you're saying could also be used in classroom generation. Are there any other questions?
But it did seem like you designed for a mobile computer rather than a desktop computer. So the fact that you could pick this up and go somewhere with it and set it up someplace else kind of consistent with your laptop type of focus.
Yes, that is an aspect that I did consider. I really consider this for the fact that statistically there are a lot of laptops and also mobile devices that are continuing to be used more commonly, and also considering the type of market that I'm having with students, especially with the idea of education and faculty when we're coming out during classrooms. We're not necessarily going to be carrying a monitor with us all the time, and therefore the idea of using smaller devices such as a laptop and an iPad. Are there any other questions? Yes.
Did you use a 3D printer? It feels like you went through a number of iterations with kind of your prototypes.
Yes. So I did use a 3D printer. I also used a laser engraver. So for the, actually, I don't know if we have our posters. In a little bit, we do have posters where we complete some of our design. But these were actually designed CAD modeling, and then those were 3D printed, and then attached. And then those were really the things I was using for a 3D design. And the rest mainly was designed and I didn't necessarily use a CAD software for that. Are there any other questions?
I'm going to cut you off. Very nice, Hope. Thank you very much. So I'm looking at a little bit of the feedback from live feed, and we don't have good microphone, so the louder you guys can speak, these darn masks kind of muffle our voices. So if we could try to project as much as possible, that would be good.
Can I put my poster board up there?
Yeah, what do you need help?
No.
Yep, all right. You got it, Hope?
I'm trying to figure out if there's like another.
You want to, let's put,
I don't know if there's like another aspect, like another test.
we'll put it on the stacks over there, we can move it around.
Yeah.
Okay. Hello, my name is Ben Clymer. I'm going to the University of Colorado Boulder next year, and my major is communications. Okay, so I created a wildfire detector, or a fire detector, with the help of Brian Burnett. Brian Burnett is a wildfire specialist. He's the president of Wildfire Specialists Incorporated in Ontario, Canada. he would be here today, but unfortunately due to COVID and border restrictions, he couldn't come. But he told me that he is off to northwestern Ontario because the wildfires have been spreading, or the wildfires have been starting and spreading very fast and are going to increase soon. Okay, so why did I pick wildfires? When I was originally tasked with picking a problem to solve or create a solution for, I was having trouble because I was trying to think in my life what problems do I face. But I turned on the TV and I started thinking bigger, and I saw that there's wildfires kind of everywhere, especially in the US, in California, Oregon, Colorado. So I thought that that would be a good problem to solve because that's an issue right now, especially with global warming, the CO2 emissions increasing and trees being destroyed. And in further research, I realized in 2020, over 10 million acres of land have been destroyed from wildfires across the world. And in 2018, over 18,000 houses have been destroyed and over 16,000 people have died from wildfires. So I thought that it was a problem that it's a big issue everywhere. The current solution, right now, the main solution is NASA satellites, at least for the US. It's a satellite. The satellite used is called a geostationary orbit satellite. It is a stationary satellite, as you can see in the picture. It stays at one point, but it has a wide range of vision. And every 5 minutes, it records smoke and thermal emissions. So it detects that, and then once it senses that there's a fire or wildfire, it sends that message down to emission control. Now, it sends it down immediately, but my expert told me that it takes roughly 20 minutes on average to get through a wildfire and to start like actually working on stopping it. And so if it's every 5 minutes, if it's sending them or detecting it, and 20 minutes to get there, that's a long time. So the fire could spread over a wide range of area and destroy a lot of trees and houses and kill people. So what I wanted to do was create a device that would be able to detect a fire or wildfire immediately and send a message instantly to a nearby source that would alert them that there's a wildfire, and then they could alert a fire station, or the source could even be a fire station. The target consumer that I had was like forest rangers, because I thought that what I wanted my device to be able to do was I wanted forest rangers to go out into a forest and put it on multiple trees or one tree around, and have that be able to detect whether there's a fire, whenever. Some of the stuff I wanted my device to have was I wanted to alert a local authority. It had to withstand like conditions like rain, hail, fire, wind, and stay in that position so it can still detect that fire and not be destroyed. I wanted it to be placed in a tree because that seemed like the easiest place in a forest. I didn't want it to be on the ground where an animal or person could step on it, and in a tree it'd be visible and easy to see. The constraints I had around it was I didn't want it to harm the wildlife, and I wanted it to be mass produced so that it can be shipped anywhere, because a lot of countries are having this problem. So if it could be mass produced and shipped anywhere, then they could fix the problem of wildfires. Okay, so for I had the device that I wanted to create that would detect wildfire, and then I had a container that I wanted to create that would be able to enclose that device and be able to be placed in a tree. And for the device, there was 4 main parts. There was the processor or microcontroller that would power each of my sensors. There was the temperature sensor, which I needed to sense temperature. And then there was the communication part, where it would communicate with another computer somewhere else. So for the temperature sensor, on the screen I used a TMP36 sensor. It's an analog sensor. it measures from negative 25 degrees Celsius to 150 degrees Celsius, so it's a wide variety. It's an analog sensor that the way it detects if there's a fire is it measures the voltage increase or decrease using a diode, and using that in a formula in my code, it spits out a temperature in Celsius. So the temperature that I had, if it detected anything over 30 degrees Celsius, it would be alerted. I started off using an Arduino Uno. I used an Arduino Uno because we've used, last year in DE we used Arduino. So I had a little bit of experience with it, so I thought that my experience could help me with the coding process. For communications, originally I had I researched, the only thing I could think of was Bluetooth communication. And so I found a sensor, it's called an HC05 sensor. That's Arduino compatible, but it was very difficult and big to use because the only way that you could connect it to something else, another computer, was through a Google Play app. And the Google Play app was made by not like a big company. It was made by a little user, and it had only been used like 20 times, so it wasn't really a good idea to use it. This is an RF transmitter. This is what I ended up using. RF transmitter is a radio frequency, so it sends a radio wave to an RF receiver somewhere else. Once the message is gotten that there has been a fire. That's the RF receiver. So for the container, originally I didn't know if I could screw into or nail into a tree a device without harming that tree. But after I asked my experts, he told me that you could, without harming the tree, nail or screw something into the tree. So originally I thought that it had to be maybe placed or even wrapped around the tree or hanging from it. So this was my first sketch. This was my second sketch when I realized that it could be nailed into the tree. I thought of creating like a circular device where the Arduino or the device could be placed into a little box and then picked up once it needed, if there was any issue or change, and then it could be put back down into the box. And then this was the idea that I actually prototyped. It was a sliding device, so you slid the bottom piece into the mechanism and slid it out, and you placed the Arduino in the box. And when you slid the piece in, there'd be a doll that would be placed in that little hole, and that would keep the sliding pieces there. And this would be then glued onto a tree. So I first modeled it in Onshape. This was the pickup container, but then I switched to the sliding piece. So the Arduino would be placed in there, and then that piece would slide into it, and then a doll would be placed into that hole to keep it in place. So from this prototype, it took me about 2 weeks to build, I'd say. I used wood, which I obviously wouldn't be using in my final design because it burned easily and would not be good to be used in a forest fire. But what I actually learned a lot from creating this prototype, because I learned that this was like way too big. What I wanted in the end was for a forest ranger to just be carrying like a bunch of these around and just be able to screw them or nail them into a tree so that they can get it done quick and they can work efficiently. Here's an example.
Yeah.
So the Arduino would be placed in and then they'd both slide in, enclosing it. So I learned that this was way too big, as I said. And I also learned that it would be better if my Arduino, if the device that was sensing the temperature was connected to the outside so it could sense the temperature quicker, so that the wildfire people could stop it quicker. So the container I actually ended up using is called a project box. It's used in many Arduino examples. It's a box, as seen there, where you can open it up and place an Arduino in, and then enclose it using screws. And this is good because it's small, a lot smaller than that prototype, and it allowed, it was portable. So actually creating the device. The Arduino Uno that I use was very big, and so I was looking for other Arduino microcontrollers that I could use, and I found the Arduino Pro Mini 5 volts, which was really helpful for me because I needed 5 volts to power my Arduino, to power my RF transmitter. This is the end picture of my breadboarding. The first little black thing is the temperature sensor, and then the bottom thing is the RF transmitter. And it has an antenna sticking out of it, so it has a better connection to the RF receiver. So for the RF receiver, I could use an Arduino Uno because the Arduino Uno and the RF receiver wouldn't be in the forest, and they could just be plugged into a computer anywhere else to receive that connection from the RF transmitter. So it could be anywhere, and it could be as big as it needed. There's also an antenna sticking out of that for a better connection. I needed a power source for my Arduino Pro 5 Mini in the container. So I decided to use coin batteries, which are small and very easy to carry around. That is the container for the coin batteries. It's wood and copper with two wires sticking out of it. The black one is the negative connection, and the red one is the positive connection. And they go into the box and into the breadboard. It's not a very good container. The coin batteries often slip out, but for what I needed at the moment, it worked. This was the coding I had for my device that would detect a temperature sensor. The top two lines are the libraries that I needed, Radiohead library and the SPI library. That was for the RF transmitter. You needed those to program that. The 35 temperature, that's in degrees Celsius, because that's how my formula would eventually get. That's what the temperature sensor would eventually get. It's in degrees Celsius for my formula. And 35 degrees Celsius is around 95 degrees Fahrenheit. So at any temperature, any point above 95 degrees Fahrenheit that it sends, it would send a message to the RF receiver. The RF receiver would constantly have a message ready that there's a fire, and whenever the sensor sensed over 95 degrees Celsius or 95 degrees Fahrenheit, 35 degrees Celsius, it would send that message to the RF receiver up to 500 meters. This is my final design. That's the inside of my final design. I needed a cord to get to the temperature sensor because it wasn't long enough to actually stick out of the project box. And so, since I wanted the temperature sensor to be out of the project, to be out and sense the air, I needed to have that cord. And I also put the antenna out so it would have a better connection to the RF receiver. There's a little video of it. The side pieces on the top and the bottom Those are 3D printed. Those are so that the device can be screwed or screwed into a tree. So a forest ranger could just carry 15 of these around in his backpack and stop at trees, and then just bring out a drill and drill them into the tree. That's the outside of the project box. Okay, so for my testing, on the data sheet for the RF transmitter and the RF receiver, it claimed that they could have a connection between each other and a message sent for up to 500 meters. So I wanted to test to see if that was true. So if each little box in a forest could be 500 meters away. And so I would back up for my test. I attached that to a tree and backed up 25 meters. And every 25 meters, I'd see if there was a message sent to the RF receiver from the transmitter. I'd have a constant message sending and see if it was actually sent. And it was sent up to 500 or 400 meters, but after 400 meters, the message was never sent. So from my testing, I concluded that in a forest, the message would probably be able to be sent around 300 meters because the trees would disturb the connection. So they couldn't travel 400 meters completely. The trees would disturb the radio wave sent between the RF receiver and the RF transmitter. For the cost, it cost a lot in the end. The cost for me was $70.30. The TMP, everything was pretty cheap, other than the project box, the shipping, and the Arduino Uno. But what's good about that is the Arduino Uno, you would only need to buy once because you'd only need to have one Arduino Uno to connect it to a RF receiver. And you don't even need an Arduino Uno, you can get a smaller microcontroller too, which anyone will work that is compatible with the RF receiver. So I figured that if you could get the shipping or the total would then be down to around $50, which is still a lot, but if wildfires are really destroying a ton of land, so spending a lot of money on them would be worth it because it'd help and fix a lot. For future improvements, that's a coin cell battery holder that just looks a little bit better and will hold the coin batteries a little better. But if I were to spend more time on this and make more improvements, I wouldn't want to use coin batteries or any type of battery as a power source. I'd want to use maybe solar panels, which could go up along the tree, and so they could store power from the sun and power the device for constantly. So you wouldn't need to change the batteries every time they died. I also, in my code, would like to eventually get to a point where it tells you when the batteries are getting low, and to have it so the RF transmitters could connect to each other, so you could have them connected to each other, so you wouldn't need an Arduino, you wouldn't need an RF receiver within 400 meters of each singular RF transmitter. You could just have the transmitter send messages that there was a fire, and eventually have that get to the Arduino or to the RF receiver. Any questions? Yeah, go ahead.
Did you do any research on whether any device like this or earlier has ever been done before?
So there was a device called an MK1 that was used. It was a sensor that would could see 360 degrees, and it would measure, it would thermally measure to see if there was a fire. It was used in, I think it's at 2014, but it wasn't very efficient because it also was not solar panel. It was not solar panel powered, so you'd have to switch a battery, and sometimes they break often due to wildlife. I think it was.
The other question was on the battery. What's a typical lifespan for a coin battery?
I bought these batteries probably in March, and they've worked every time I've needed them to work, but they won't last very long, so that's an issue.
Especially outdoors.
Yeah, they need to constantly be changed, and that's another problem for the container, as they're held right now. Rain would destroy them. Yeah.
Did you incorporate any concept with smoke detection along with the heat?
I didn't incorporate any smoke detection because if there was smoke detection, that smoke would be above 35 degrees Celsius or 95 degrees Fahrenheit. So it would be able to detect that. Yes?
Hey Ben, nice presentation.
Thank you, Mr. Gill.
One quick question is, do you have a time component? So in other words, do you have to detect above 35 degrees for more than a specific period of time? Or is it from the moment it detects greater than 35 degrees it triggers?
From the moment it detects 35 degrees or 30 degrees Celsius, it triggers immediately and alerts the RF transmitter to send that message to the RF receiver.
Okay, thank you.
Any other questions? Yeah.
Did you figure out the RF receiver, how it might handle multiple transmitters?
Say that again, sorry, I can hear.
It sounded like you had kind of one transmitter and one receiver.
Yeah.
But in a real example, I think you need lots of transmitters going to one receiver. Could the receiver be able to figure out which guy sent the message in and said to the fire here as opposed to the other 30 that weren't?
So, that would be a good point. That's what this also doesn't do now, is it doesn't actually alert, or having one does alert where it is, but I'd have to find a way to let it know what location it is, longitude, latitude, to actually alert where the fire is.
So literally it's just a yes as opposed to some kind of ID that it's sent in that.
No, you just know where, you just know that you get the message, you don't know where it's coming from. Any other questions? Sorry.
All good?
Yeah.
Thank you, Ben. Want your stuff over? Where do you want it on the table?
Just facing it.
Oh, sorry.
Alright, so my name is Tim Larson, and the concept I wanted to do my project on was automated inventory. So what got me interested in this concept was I worked for a couple of months at a retail store, CVS, and one of the jobs I enjoyed doing the least was they made us do manual inventory somewhat routinely. Not a lot, but it was enough that it was annoying because I could see it was definitely useful for data collection purposes, but it just took forever and it wasn't very accurate, so it wasn't essentially very useful for them or the employees. So basically the problem that I decided to focus on was making a better inventory gathering solution, preferably automated. And the problem was that stores spend a lot of money in the form of like either they install huge systems, like for instance Amazon Go is full of sensors. They only have people stocking items, but they know where all the things are. But they don't have many locations because it costs a ton of money to fill a store with that many sensors. Or they have to go with a manpower solution, which is inefficient in the use of their employees' time and subject to a lot of human error. Another aspect of the problem is that whenever you have error, especially with stores like supermarkets, which have high product turnover, that's lost revenue in the form of products that you didn't sell for whatever reason. So the basic design idea was to reduce what's called shrink, which is basically just anything that takes away from your profit that isn't normal operating costs for the store. So specifically, not like theft, which is also shrink, but like the more inventory management aspects of like over-ordering items or under-ordering items. So the two problems I focused on for my automated solution to this problem was first how to collect the data. Specifically, I wanted to focus on the inventory and how to constantly collect how many items were on each shelf at specific times of day. And I wanted to do that with a different type of sensor, but I wasn't sure which because each had its own drawbacks and issues. A couple that I considered were a distance sensor solution, either using like an infrared or a ultrasonic sensor, or the other option that previous designs that were similar decided to use were RFID tags, but I didn't feel that was a good solution because it's overly complex and it means that small stores couldn't implement it because they'd have to have their own supply chain where they would attach RFID tags to every single one of their products. So it would require a lot of more change than I felt was necessary. So as far as moving the sensor, I ended up going with the ultrasonic distance sensor. And I wanted, instead of putting a sensor behind every single object on like a grocery store shelf, I decided to move it along the shelf. And so then I was faced with the dilemma of how to do that. And originally I wanted to have like a pulley or a gear design, but I felt that that would be overly complex. So I eventually went with, it's essentially a threaded rod that moves the sensor housing along the track behind the items. So the way I was going to do this was with Arduino, like a lot of the other projects here, and just some soldering of the various components. And so the earlier versions, I just started with detecting how much distance was between the sensor and an object of a known width. So that's that there. And then I moved on to having multiple sensors, but I started getting a lot of errors with possibly them interfering with one another. So I decided to go back to one sensor and just focus on getting one shelf to work at a time. So you can see there in the top left, I've essentially just got an Arduino with the motor shields controlling the motor on the far right to move the sensor right and left down the shelf to detect each object. And then I've got a switch on either end to essentially set the limits of the work envelope, I suppose you'd say. And that essentially, there's more parts of the code, but the important bits are moving it to the origin each time, because I was thinking of making a coordinate system, but I felt it would be overly complex and time consuming. So essentially, I've just got some incrementing some variables, and then every time before it goes to detect an item, it goes back to the origin until it hits that switch over there. And then part 2 is once it's at the origin, it moves, well, there's a part in between, but it moves to the, where the first or second object is, and then it detects it with the sensor, and then it first calculates the distance between it and the furthest back object. So this design does have the disadvantage that if everything isn't squared up like it's supposed to be in a grocery store or a retail store, it doesn't necessarily detect the right amount of items, but you are supposed to do that as an employee, so if people do their jobs correctly, it should work. So it detects the distance between it and the furthest back item, and then it subtracts that distance from the known shelf width, which gives you essentially the distance on the other half, and then you divide that by how much depth whatever item you're detecting has, and that theoretically should give you the quantity of items. So financially, this came down to, it's kind of a game of how much, because theoretically you'd want to implement this on a large scale. And so it came down to, with a single setup, about $16.58 per foot, which sounds like a lot, but you can theoretically save a lot because shrink is, for grocery stores, they have really small profit margins of only about 1% out of their total revenue, because they have a lot of items and a high turnover, so they think as long as you put enough things in your basket, they're pretty much fine. But that means, fortunately, that the more you reduce your shrink, it directly goes to profits. You don't have to reduce it by that much to drastically increase your profits. And then also, this design, you can stack motor shields. Essentially, each motor shield is another shelf that you can do. So this design, you can stack a lot of them on top of each other, and it essentially gives you 768 outputs before you have to add another, or sorry, not 768 feet, not 768 outputs of shelf feet. This one design could theoretically work for a maximum of 6 feet, and so that brings the total down to 965, which is a bit more reasonable. So in conclusion, the design is fairly simple and pretty scalable, with a couple of fail-safes with the maximum and minimum switches. Unfortunately, it's a little bit expensive, and currently, in the original design, I wanted it to export directly to Excel, so that you could easily access it from like a central thing in the company if you had a large company. And there's no coordinate system, which means it takes a bit of time to go back to the origin each time. And so in future, I would definitely modify those two things. So as far as the Q&A, the questions I anticipated before actually getting into it was how I actually attach it to a shelf, because you probably wouldn't want to actually screw it into a shelf. So this was just for demo purposes, but most grocery stores have what's called gondola shelving, which is just the racks that go in, and then they have the pegboard behind where they can hang various items. And so I would probably attach it via the pegboard, so you could hang it directly above whatever shelf you wanted to. And then the intended use for this is local and independent retailers, because large-scale chains would probably want to develop their own solutions. But smaller stores, not small like mom-and-pop shops, but like smaller supermarkets that don't have their own supply chains, and therefore other solutions aren't as viable, I felt it would be useful for them to reduce their costs and therefore increase their profits. And that's it. Any questions?
So would the device be visible to the consumer?
Probably yes. It would be in the back, and that's another unfortunate thing because that means you have theoretically a little bit less shelf space. But I felt it was compensated for the fact that you could have constant updates on your inventory.
And then tampering?
Yeah, sure.
Did you look at different shapes, like circular cans versus square boxes? Because the circular cans, if it's measuring with that clinic opportunity,
So you're saying the shape of the object does it affect the sensing?
Measures the distance on
Yeah, I did use curved objects on
Right.
it. Seemed it does widen a bit the range. So if it was like a really narrow item, that would be more of a problem than necessarily the curvature of the object.
All good? Anybody else?
Camera based then?
Oh, sorry, it's a ultrasonic sensor, so it just does sound waves.
Okay.
And then, yeah.
So that's cheaper than a camera.
Yeah.
Okay, thank you. We're going to take 5 while LB gets ready. So if you need to go to the restroom, grab a drink or whatever, please do so.
Yeah.
This is weird. The live stream is about a 20-second lag, so I can see myself from 20 seconds ago. It's weird.
Project for next year.
A time machine? Yeah. What's that?
You went all the way to time machine.
What do I care? It's them that has to do it. All I got to do is try to help them.
Set the expectation high.
There you go. Do we have everybody back, or are we?
My dad.
Your dad's still out?
Good start with that.
I think we'll wait for a few minutes. We're still waiting for Jacob's dad, I guess. Unless he decided to leave before Jacob started, so maybe there's that too.
We want to be the first.
So I did this for training 22 years ago, and the night we had to do it, we did it in front of engineers from RIT, and the rule of the day was keep asking questions until the person presenting said, I don't know. and so I presented, we were living on campus, and so it's always a formal or casual business or whatever. My snap to my pants broke, and my computer stopped working, so I was in panic mode for the whole time. So this is going pretty smoothly. All right, I think we got everybody now. Good?
Hi.
All right.
I'm L.B. Burkhart from Skaneateles High School. A senior. I took all of the engineering classes. Actually, I didn't take DE, but I took most of the engineering classes here. And next year I'm on to Alpha State for electrical engineering. That's the plan. If at any point in this presentation you have a question, you just raise your hand and I'll try to answer it. And this is my presentation on the deployable airbag vest for alpine ski racing. So first off, why do I care about this? I've been ski racing for over 11 years, and I know what it feels like to crash. It is not fun, and I've seen a lot of people have very serious injuries, and my goal with this is to try to minimize that as much as I can. So, introduction. The sport of ski racing is associated with high risks of injury. Many implements try to bring a solution to this, but many bring their own risks associated with this. One of these prior solutions is B-netting. This is the most universal used option. They're lined the sides of the trail, and they're collapsible nets that sort of work like a crumple zone in a car, slow you down. But the problem with this is they don't always bring you to a complete stop. You can slide underneath them, and trust me, when you run into these nets at 60, 70 miles an hour, it does not feel very nice. So, the problem statement. In ski racing, being a high-risk sport, contains lots of injuries. A large percent of the most severe injuries are from the skier losing control and crashing into objects off the trail. There are some solutions to this, but all of the fully utilized options still place the skier at risk. The design statement. To design a solution to help prevent alpine ski race injuries related to off-trail collisions. This solution will place minimal injury to the skier while still maintaining effectiveness to the original or existing units. So, some research, baseline started it. Some research about my problem. Most of my research included just identifying major risks that are associated with ski racing, so I could try to find out how to solve it. Organizations like the Kelly Bush Foundation, which is an organization dedicated specifically to preventing ski race-related injuries, was helpful to finding some statistics. So, deciding on a solution. I did two major iterations. First one being a sort of like big net structure, and the second one being the airbag vest, which I followed through with. So some other ideas, which are similar to spitballing at the start. I had a sort of spring-loaded sort of netting system that flaps on top of you to try to bring you to the complete stop first. At the airbag, I had the sort of snow skirt design that I thought of to try to sort of get a little bit more crumple, and the bottom of the actual tower thing I'm about to show. So, continuation with the net structure. This is what I've spent the first good amount of time on thinking of designing. So this is a rough sketch when I just first started. The major idea is that it's a tower with a netting, sort of like bee netting, attached to it. This would allow sort of the crumple, the like slowly deceleration of a bee net with a hard stop so you wouldn't continue going off the tray, which causes a lot of injury. This, I'm not going to spend too much time on it. It's just some trig and some force equations just to try to see the math of it if it would work. And the math did work, but why didn't this work? When I was doing the trig and everything like that, I found that the net structure was going to have to be like 15, 20 feet tall, and that is very impractical to build in this sort of environment. And also, this just isn't really where I wanted to go with the problem. So my next design was sort of a airbag vest design. You can see on the right, this is just sort of my first ideas, just starting to throw that out there. You can see there's one idea that I didn't fall through on the contacts in the bottom of the boot. And to the left, you can see sort of what inspired it. Once I was starting and researching on this, I found another product that's used for motorcycles that it's sort of like an inflatable vest, but it uses a gyroscopic sort of sensor. So if you fall off, then it deploys, which wouldn't work for skiing because you're often like in very wild positions, and also you can fall but still be safe. And I don't want it to deploy then, because the most common crash is just leaning in on the side and sliding out, which isn't much danger at all. So here's some photos of my product. Here you can see this is sort of the electromechanical aspect of it on it that I attached to this belt. You see? From here you can sort of see what the main aspects are. It's a 16-gram CO2 cartridge, like this, hooked up to a solenoid valve. And I have two switches on here. It's a head right here, sort of a kill switch. Not sure if you can see the LED light on there. Turns on and off. And a deployment switch. This would be connected to your ski boot. So the way the ski bindings work is that when you apply a lot of torque, like in a crash, the ski pops off to try to save your legs from unnecessary injury and torn ligaments. So major crashes, 95% of the time, your ski pops off, and that's when this would deploy. Here you can sort of see inside. To the right is the Arduino Uno I used, and has a breadboard shield on it to make the wiring a little bit easier. You can see a transistor on that white breadboard. And to the left, you can see the batteries I used for the power supply and the solenoid valve. And one thing I ran into is I could have just used, there's small 12-volt batteries that I could have used that would save a lot of space. But the solenoid valve takes a lot of wattage to run. So it would run out in 1-2 deployments, and that would be a problem. Here you can see some more pictures of just the vest that I have going on. From the left you can see sort of the whole thing. It's pretty big and bulky, which is not too optimal, but this is more just a proof of concept to move on from here. So here's a bit of a schematic for you. Again, using the Arduino Uno for the microcontroller. And the big thing with this is it sort of has two circuits, as a 5-volt circuit and a 12-volt circuit, because the microcontroller runs off of 5 volts, but the solenoid valve runs off of 12 volts. So keep that in mind. But so sort of the play-by-play is if the kill switch is off and the deployment mechanism is activated, those are the requirements it needs to deploy. What happens is a signal is sent to the transistor, which acts as a solid-state relay for the 12-volt circuit. This allows the 12-volt solenoid to connect to ground, completing the circuit, allowing the CO2 cartridge to fire. You see right here, CO2 cartridge. As soon as both those requirements are met, this valve opens and deploys the air out of it into this tube, which inflates the vent. So, creation of solution. This is sort of my fabrication techniques for the vest. For the airbag, I used heat transfer vinyl, and I used an iron to melt the seams, making it airtight. You can see the photo on the left. This is sort of when I first got started to see how it worked. To attach the airbag onto the vest, I just sewed it on the seams. And for the electronics, I attached it to the belt, again, mostly as a proof of concept, just so I have everything there. If it was fully utilized, I would put it into a smaller form factor, most likely on the back of the boot, where it would be less intrusive. So, for the electric and mechanical aspects, again, I used an Arduino microcontroller. It's a very name brand, and again, we have experience in it. It uses C++. It uses a breadboard shield for wiring. You can see that on the left. It sort of goes on top just to make everything easier. I had a kill switch and deployment switch, and an LED monitor that you might have saw earlier. So, again, play by play. How does this work? So when the ski falls off the boot, the deployment switch is triggered. The solenoid valve releases the CO2, and that inflates the vest, preventing the injury. So demonstration, I have a bit of a video. This is just off the air compressor, so you can see it inflating. Sorry. There we go. So this is the point where I have to say, unfortunately, when I was outsourcing the parts, I found an unreliable source, and the solenoid valve that I bought is cannot handle the pressures that the CO2 cartridge delivers. So unfortunately, I cannot get it as the way it is to fire. What I would need to fix that is a pressure regulator, which I didn't have the time to outsource for this presentation. So for testing, I inflated the airbag and I used a veneer force sensor. I built a 6-inch by 6-inch platform on top of the sensor and dropped objects of known mass 12 inches up the platform, with and without the airbag. And I measured the difference in force. That's not work. So results of testing. Here you have a little bit of an Excel sheet. You can see because of the sensor I was using, I was not able to use large masses, so I used a 0.325 pound mass and a 0.65 pound mass. And I did 3 trials for each, and you can see the results on there. And I took the percent difference with and without the airbag. For the 0.325 pound, I saw a 30% decrease in force. And for the 0.65 pound mass, I saw a 26% decrease. And you see that in the graph too. In blue it is the no airbag, and in red is the airbag. So, general conclusions about this. I believe it's a successful proof of concept, but it has some fatal errors. If I were to continue this project, I would have to add that pressure regulator so the solenoid would fire. I would have the airbag cover a larger surface, maybe even lower body, because that's another large place. And I would shrink and relocate the electromechanical aspects. I would do this by using a smaller microcontroller, soldering it onto a PCB board, which is a printed circuit board, and again, probably locate it somewhere on the back of the ski boot. Okay, does anyone have any questions?
How do you know that it inflates fast enough to prevent a fall? Like once your boot is coming off and it's triggered, you're in trouble on that.
Well, actually, right here, because the solenoid doesn't work with the CO2 valve, I soldered quickly onto that. So when I deploy the deployment switch, that should light up immediately. You see that? Then turns off again. So that concludes the sort of electrical aspect. And when you're looking at the actual airbag inflation, the 16 gram CO2 cartridges are pressurized at 820 psi, which is very high. And that will, when I had this hooked up with a fully pressurized, and I unscrewed it, it all released in, I think it was less than a second, like less than half a second. It was very fast. Anything else? Yep.
So is there concern, so it straps onto your body, right?
Yeah, it straps on your body.
And you run up to 6 grams, you inflate it with the CO2. Is there a risk of compression?
Compression on yourself?
Correct.
No, I actually had it worn while it was fully inflated with the air compressor, and I specifically sewed it on with it not tight, so it had room to expand.
Okay.
Yep.
Where are the majority of injuries when skiers crash? What part of the body gets injured?
So the majority of the crashes is in the knee area, but another large percentage is in the upper body because thinking when you're crashing, a lot of the impact, and I personally have experience with this. A few years ago, I injured my sternum in a crash, and that took over a month recovery, and that could have been easily solved with something like this. Anything else? Yep.
Yeah, you mentioned that there's an existing design that motorcyclists use.
Yeah.
Is it also CO2 activated?
Is it also what?
Is it also CO2 activated?
I believe so, yeah. Again, I showed the airplane life vest earlier,
Yep.
and that had that too. That's sort of where I got a lot of the idea for where to use the gases, both the motorcycle one and the airplane life jacket. Yep. Anything else?
What's the typical time between when you crash and when you actually hit something to hurt yourself?
So a lot of the time is there are some crashes where you can catch an edge and go down immediately, but a lot of the time you're moving at such high speeds that when you crash, you have a little bit of air time. So common in a crash is you cross your tips or something, or you lose a ski. You're up in the air for a while before you actually hit the ground. In most times, or before you're on your feet for a bit.
So as a follow-on to that, does it require you to lose, you're going to put the sensor on one or both bindings?
I was just, both bindings. Yeah, one on each leg. I only wired it for one, but it would be an easy, just an easy another soldered on. Anything else?
Okay. Go.
So obviously skiing aerodynamics is key.
Yeah.
Right? So have you thought how you could slim down design to make sure that the thing is really, really thin? And
That's a really good point because all racers wear skin tight suits while we ski, which is very cold, but it is faster. And I haven't really thought too much about how to put into that, but I mean, this I just used an old vest I had lying around, but you could make it a lot thinner. I was just putting like a piece of like a vinyl clothing or something like that. A lot of people wear, they're called stealths, they're padded shirts on your arms. A lot of people wear those over their speed suits too, which I feel like if this was fully optimized, it would have a similar form factor. So I feel like my design isn't anywhere close to aerodynamic, but I feel with a lot of improvement it could be.
And then you think about the head aspect of it too. I mean, it seems like there weren't helmets anyway, so you could put something similar up there.
Yeah, absolutely.
Okay, thanks, Elby.
Slow descent.
That was pretty smooth.
Alright, so I'm Jacob French. I'm going to Clarkson University for engineering major. I've taken all 5 of the LTW classes here. I'm currently in the engineering design development class and principles of engineering class. I chose for my project, I went with the modified parallel clamp. There's a picture of it, as you can see right there. That's the final product. And my 2 experts are Gregory Garnett and Joanna Bartley. Sorry for pronouncing it wrong. And then I contacted my experts. I contacted Joanna through the Clarkson alumni program. She was an engineering management major there. And I reached Gregory through one of my aunts that is in a rock band with him. And he works at Lockheed Martin. To start, I started with the design group. Sorry, I can't read that. I'll go into more depth with the picture in a second. I chose this problem partially because throughout my experiences through all the PLTW classes, I'd always have some sort of challenge with the clamps. I could never keep them parallel. I'd spend probably like 5 minutes trying to get them parallel perfectly. And I think there was a solution that I wanted to be like accessible through novice workers. For a client, I chose technology classes in Yale schools. So this is like specific. And it's target consumer, like novice woodworkers. And my problem statement is, in the lab, it's hard to get devices even with each other. It's difficult to keep the clamp parallel while moving the clamp precisely. For the design statement, the device will make it easy and quick for the users to tighten and loosen the clamp while applying equal pressure to both sides of the block. In the criteria, the completes intended function is ergonomically comfortable in the user's hand. I went with general constraints that would be able to apply 10 newtons of force, which would generally would be apply enough pressure to mold, to fuse 2 parts together with wood glue. And can withstand a 6 feet drop. I don't think I need to demonstrate it right now, but I've dropped that thing numerous amount of times, and it's somehow still here. My Gantt chart, which is a general schedule for my tasks that I'd like to see on schedule. And throughout my Gantt chart, I kept it pretty broad with research, sketches, modeling, fabric testing, and presenting. For the most part, I was on task for all of it. The testing, I probably left a lot of time for it, not enough time for fabricating. So I went through several trial and error phases when I was trying to perfect the design. The research, what I researched existing clamp designs, other versions of clamps or other models. There was also a parallel clamp that solves a problem, but I'm going for a more usability of it, and it can get parallel. But I also wanted to be able to take out the middle part right here, so I can add more fine tuning. So I'll get it parallel and be able to close it in or close it out. And then this is a video of me in the research phase when I was trying to figure out how the clamp worked. That basically shows that there is a method to keep a parallel clamp perfectly parallel and still move it pretty efficiently. But it's a skill that some people can do and some other people can't do. And it's also it's also, you have to have, like, to know the skill to be able to do it. Through the ideation phase, I started sketching out possible solutions. I was trying to visualize a way I could make it work, like, effectively. And the first idea I had was I would have 2 gears, and they would, like, move the ends of the rods together. And this is all recorded in my engineering notebook. Other sketches, I was thinking of more like a platform that I could set the clamp in and move it. Most of my ideas there included gears because I thought that would be the most easiest way to find to have uniform motion that would translate over to another rotational part. Through modeling, my first idea that I went with was the gears would be on the outside and it wouldn't affect the design of the clamp at all, because I was trying to think of a way that I could take a regular clamp and find the cheapest and easiest way to make it into a clamp that's easier to use. This is the same clamp as this one. This one was the same clamp as this one, but this is one that was modified. For the first ideation, it had the conceptual idea of how I wanted it to work, and it was based on the sketches. And the second ideation, I had to come up with the second idea because the first one wouldn't necessarily work because there's nothing constraining the top rod down, as when it would move, it wouldn't work. It would also create linear motion. So the rod would move downwards or upwards and would move out of the path. With the second ideation, I added the rod through the middle so the gears wouldn't go anywhere. And then I put these blockers, I put these blockers on the sides of the middle gear so that the gears would stay aligned while they were rotating. Also, I created these on Onshape, which is an online modeling website that we used because we switched to online modeling during COVID because it was easier. We could do it from home as well. And through fabrication, I was talking about how I had the trial and error phases. I had to create 3 different versions because I wasn't satisfied with how the design worked. The first solution, I had a wooden gear, which was right here, and then the second one I had a 3D one, and then I modified the 3D one to be my final product that I gave today. The first prototype, which is the wooden prototype, I chose wood because it's an easy material that we have in the lab, and it would be flexible. If I have mistakes, it wouldn't take long for me to make new parts, and it wouldn't be an expensive material. And overall it worked. I was actually able to get the clamp work with the wooden gears, and I was able to create grooves through the rods with the gears because it was slightly better. And then the laser, there's inaccuracies created with this. This took me probably the longest because I couldn't get the measurements correct because the laser engraver were actually making the sizes of the gears a little smaller than I was putting in. Also, it broke easily. Some of the gears right here were broken because it was fragile. My second prototype, the 3D printed prototype, it was made through thermoplastic materials, so I was able to heat up the rod, which is a double-ended screw rod, and I was able to heat it up, and it created a groove right here, which was it's rotated on, and it would be tight in place. And the gear sizes were more accurate, so I was able to figure this one out a lot quicker with less trials. The But the only problem is when they would start rotating, this gear would go to the left and this gear would go to the right because it wasn't in place all the way. For the final prototype, I added a taper pin right through here, which I'll show on the next couple of slides. And I changed the blocks out because there was inaccuracies that created because of the holes they weren't the same distance away from the side, and they had different things. I'll show you this. So this, what I'm talking about, the taper pins, is it would go through the rod, right? The rod would go right through the double-ended screw right here, and like back here, it would show how they would go right through here, and this created sort of rotation that was able to these were fused together. And this one was the middle gear. It had the blockers on it so it would stay in place. I also filled the sides of it, so I was able to fit the gears in when I was making the model together. And this is the taper pins. They're 12-inch steel taper pins, 12-inch long, with a 1/2 inch long. With a large end diameter of 0.063 inches. So a pretty small hole. It goes to the rod and keeps the gears together. And this is where it goes through right here. And there's like a hole right here through this metal rod. And this is what it would look like on the inside. I have a video in case I didn't have the model. But that's the earlier version I had of it. But basically, it works just like a regular clamp. Like I can do this. And I can also close it this way. Like how this one was done. But I still could just move one side and it would rotate just by itself. And what I was talking about how this came out earlier was because I was an intended thing was to have this loose so I could take this out and I could move this out so I could create an angle if I wanted to have an angle. But the angle wouldn't be as great as this one because I made the holes smaller right here, which is why I switched the wood. Because it created more inefficiency when the holes were bigger and there's more room to move because they wouldn't stay exactly parallel, and then the thing would stop and it wouldn't budge. That was a major problem during my fabricating, was that there was inaccuracies created through that. And that was why there's a lot of trial and error. For the cost of creation, mostly I used materials that were found in the lab, other than the taper pins, which I got on my own. The wooden clamp was found to be about $7, and the 3 plastic gears were $15 which I found on McMaster, the pricing. They were made of thermoplastic material, so I accounted for that as well. And the taper pins, the 25 set of them cost $6, so in total it would be around $28. And for testing, I tested how fast the clamp goes in comparison to open and close in comparison to an unmodified clamp. How I did that was I would set these at specific positions, and they would be the same distance apart. And then I would have someone time them how fast they would close and how fast they would be completely parallel to closed. And in conclusion, the modified clamp is only a little quicker. It's about 8 centimeters per second faster than the unmodified clamp. These are the graphs. This is the graph of the traditional clamp. This is the graph of the modified clamp. took, I did several trials. I did 15 trials. And then analysis. I would like to have like no design change to the clamp. Instead of having like a hole go through here, I'd like to be able to just add it onto a clamp. And I want it to be easy to use. And it meets the design criteria because it works exactly how I wanted it to. And I think it would go good in like a lab or something in school. And it easily can be parallel. It can be like easily switched to this. I probably wish it was easier. And I wish the rod didn't fall out. But it has some improvements to be made, but overall I'm happy with it. This is closing. I'm closing. Thanks. But do you have any questions? Yes, Elby?
I know it works next to you for this whole project,
Yeah.
but I never understood how the paper clips work. Is it just a rod with a larger diameter and a smaller diameter and
Yeah.
you shove it in there?
Yeah, it goes through the rod. That's also another thing I didn't point out is that these are double-ended so that the threads go different ways, which is like why the clamp works. And the gear motion, so when this one, the top one rotates clockwise, the middle one would rotate counterclockwise, therefore would make the bottom one rotate clockwise again through like gears, which is translating the rotation. I got the. Do you have any other questions?
Okay, thanks, Jacob. Oh, did you have one? I didn't see it.
On the testing,
Yeah.
you just had a human
Yeah.
doing it.
Yeah. I know.
So testing variability in human nature.
Yeah, I did the rotating method through here with both of them.
So you had a single, it was just you doing it,
Yeah.
and then somebody counting it.
Yeah.
But
Yeah.
you kind of shortchange your goal is to make it easy and efficient to just use it with one to get it parallel.
Yeah.
Testing kind of,
That's true.
it just seems like you achieve the goal because you can do it with one hand and it's parallel by nature. Just to do it as fast as you can wasn't really the goal of the project.
That's a
Seems
good
like
point.
you overachieved because you definitely
Yeah.
killed it in terms of what you were trying to achieve in terms of making it more convenient, one-handed, and be parallel all the time.
Yeah.
Pretty sharp.
That's a good point. Yeah, I think I should do that next when I do more testing on it.
Good? Thank you.
You want your votes, Chris? No, we shouldn't.
Front, right.
Try to stand over here. Hello everyone, my name is Matthew Campbell. I worked on this project called Real-Time Melody Generation along with these two. First is Nate Richardson, who's a sound engineer from a recording company in Ithaca. And Claire Evans is a member of a band who I consulted during the early research phases of this project. So, the thesis, what I started with this project was this directory, making music composition accessible. Because right now we've observed that there is a skill barrier to music composition. The first thing, most people enjoy music. You probably agree with that statement, or you know. And all that's required for that really is the ability to hear. So most people enjoy music. Some people, fewer than them, enjoy music, perform music. And if you think about why that is, because performing music requires consistent practice, it requires discipline, formal training in most cases. But you still may know a musician or so, a member of a band, you may play an instrument yourself. Even fewer people write music. And that's because to write music, to compose it, is to have all of the above, as well as functional knowledge, at least, of music theory, of different compositional techniques, of existing works, and even more. So, out of these three, writing music is the least accessible. It's the highest barrier to entry. So my project was to somehow reduce that barrier to entry, make it more accessible. So let's talk first of all about what exactly is the process of musical composition. Generally, I don't know, some musicians may disagree with this, but you can think of any melody, any piece of music, as melody and harmony. And those of you who can read music, may recognize this bar here, or these four bars actually, as Twinkle Twinkle Little Star. Right? Twinkle Twinkle Little Star. And so, on the top line there is the melody. That's the part that if someone asks you what Twinkle Twinkle Little Star sounds like, you'd likely say, or hum, or sing, something like that. That's the melody. For any song, really, that's where the melody comes from. It's what you remember. It's what you say in your head after you hear the song. And the bottom line is called harmony. Those are chords that go along with the song. Those are, they contribute to, I guess, the mood of the song, but really the melody is the main part when you compose it. So step one, for most composers, not all of them, but for most, is to write a melody. And this is the part that is deceptively difficult. So with that, I began a design brief. Main sections here, the target consumer for this product will be music students and teachers, musicians, hobbyists, piano composers specifically. And the problem statement here reads, for students, teachers, instructors, and professionals in the field of music composition, creating original and unique melodies can be one of the most difficult parts of the process. Composers should be able to access a simple and reliable way of generating melodies and just applying some musical parameters of their own. So the design criteria, based on that problem statement, is one, utilize the base melody, the shortest 7 notes long. It will maintain the same key, time signature, and tempo when generating the melody. You can record directly from a piano in real time. And then output an audio file that can be played by the device. Design constraints, as my classmates mentioned. First of all, it should be completed by the end of the school year. I shouldn't be in contact with Dawson from college, probably. It should be able to be developed at home. That's due to COVID restrictions. Obviously, I don't know what kind of lab access we could have going into the end of the project. So that's why my project is mostly software based. And then total expenditure, I set at less than $300 as the cost constraint. So my initial research, and I won't go through all of these, but here are some, people have tried to do this before, and here are some examples of that. The first one, the most prominent one, which will appear throughout the presentation, is Google's Magenta. Magenta is the umbrella term, the name that Google gives to its open source machine learning software. So anything involving art and music for Google and software is going to be Magenta. Usenet, I believe, is a Elon Musk venture, one of the many, that is able to replicate the style of composers in long form music. So another interesting use of machine learning. Down here, Yacht, the fourth one in there, is actually a band that has tried to implement some software-generated melodies in their own music. And in fact, Claire Evans, one of who I mentioned that emailed during the research phase, is one of the members of Yacht. And she told me about some of the strategies they use to implement machine learning in their music. So a little more technical here on this side, what exactly do I mean when I say machine learning? I'm referring, in the context of music at least, to LSTMs, which is a type of ARM. So LSTM just stands for long short-term memory. And in the context of machine learning, that is any model that is used for sequential data. So, and when I say sequential, I mean things like language and music. So if you think of language, those are words in order, and music, notes in a specific order. Sequential data is dealt with by LSTMs. A second possible solution is something called a Markov model. Now, a Markov model is actually a statistical model that is also applicable to sequences because it makes predictions based off the previous state. So in a musical context, that would mean trying to predict what note comes after a given note based on the previous note. They're used a lot in things like predictive text and things like that. So based on a bank of data, what word is going to come after the current word, when you see little suggestions about the keyboard when you're typing, those are Markov models. So I thought that may have been applicable. At the end of the day, I went with the LSTM method, but that's part of the research. Preferred programming language. So there are some options, but Python is actually the industry standard for data science or machine learning for the application I was looking for. That's also the only programming language I know, so this is one I went with. So Magenta, okay, just said on the previous slide, Magenta is Google's flagship music machine learning open source database. And it has some pros here. It's documented, it's updated regularly, it's open source free, and it's relatively simple to install, not simple to install, relatively. It's not that well documented. When I say it's documented, I mean all the code is available, it's readable, there are some tutorials, but it is not. There still needs to be some digging done to understand how something's working. The community is relatively small. I posted on the forums a couple times during this project. It didn't get that much traction. And then it's dependent on certain packages that require Linux. That's why I have this desktop here, because I don't have a Linux machine. I borrowed this one from the school. But I did choose Magenta. So technical details again. The programming language is Python, version 3.5.3 if you're interested. The operating system is Linux. The distribution is Ubuntu 20.04. Some packages, this is the programming. This is for reading audio. This is for machine learning. These are for math. This is for data visualization. Hardware, the desktop right there, you can see it's a standard HP school computer running Linux. And then the microphone is a USB-A microphone and then speakers. Nothing really special about either of those. It's a USB microphone and a Bluetooth speaker that I'm connecting via aux. So to understand this project, I've decided really should think about it as just converting data into different forms, so that eventually I can get an output file. So here's the general form for how I initially planned to do that. I started with data in the form of raw audio, literally sound waves, vibrations in there. From there, I had to use an audio to MIDI converter to get what's called a MIDI file. That will be the input file to Magenta. Now, MIDI is a data type used by computers to represent musical data. So sound engineers be familiar with MIDI. Anyone who's worked with music, be familiar with MIDI. It's just a way for computers to understand music, because computers don't by default understand vibrations. So MIDI files are ways to store notes. So I go from raw audio to MIDI, and then to another data type called a note sequence. Now a note sequence is actually very similar to a MIDI file, but it exists only within the Python programming language. And the reason that we have to move that version is that is the input type to the model that's going to extend the input melody. So I start with the raw audio, someone playing, say, 8 notes on a piano. And then through all this software, we eventually get to a form that can be input into Magenta, which will extend it based on machine learning and get the output file. That's what I'm looking for in the end of it. So, as proof of concept, I tried this. And hopefully you can hear, but this is a melody I wrote for the piano. And then I looked online for an audio to MIDI converter, because that's the common thing people need to do. They need to convert between audio and MIDI. So I found one online, and I got this. That's not right. Alright, so I know that was difficulty here, but basically, it wasn't exactly what I played. You can hear that there are notes that weren't there, there are lots of octaves that weren't there, jumbled notes, things I didn't want, right? So that's not, it was a bad conversion, I didn't want that. But to proceed with this, to complete the proof of concept, I manually created a note sequence that's supposed to be equivalent to this audio. And by manually, I mean I literally wrote this note for this long, here to here, etc. It's going to be a little slower than the initial melody because I didn't understand how tempos work at that point, but it's happening. All right, and then I supplied that to the Magenta model and got this result. So everything past roughly that halfway point was generated by the software based on machine learning. I didn't write it. It's based on only the input. So that's what I wanted to do. I wanted to get from here to here without having to manage anything with it. So this is the product. This slide really is everything that I did. It's supposed to take raw audio, feed it through a custom converter that I wrote into a note sequence, which goes into this model and generates an output file. That's the goal. So, written in another way, here are the requirements. Here's everything I want the software to do. 1, discern notes from sound waves. 2, detect the beginning and the end of a melody. 3, determine the location and the length of rests. 4, convert all of that into the note sequence format, and then finally supply that to Magenta and play the output. So, I can start working with waveforms. The first form of the data, like I said earlier, is raw audio. It's just sound waves, and that is what's shown here in the blue. This is a plot of just something I played. I don't remember exactly, but it's sound. This is wave that has a given frequency, the frequency that changes at different points. And this blue is what I need to get to a note sequence format. Just if you want to have labels, this is audio samples and this is decimals, basically, well, sound function. So let me talk about the note sequence data type. Like I said, it's the input data type for Magenta's continuation function, and the important thing about note sequences is that in a note sequence, every note is defined with only 3 things. The note start time, its end time, and its pitch. So if I can take this data and then find the start time, end time, and pitch of every note in there, then I will have achieved my goal is. So, before we continue to explain what I mean by certain things and how audio is read continuously. So the point definitions here. An audio sample one is a reading of sound pressure at a specific point. This is analogous to one frame of a video. Okay, you know a video is a set of pictures, a recording is a set of audio samples. So a sample is like a frame of a video. Now a chunk is a group of samples. And samples need to be grouped because samples are taken at very, very high frequencies. And if I want to process data that I want data in chunks that are smaller than a second but larger than as small as a sample is. So anytime I create a new audio stream, I'm using these two important parameters. One is the sampling rate. That's the number of audio frames captured in 1 second, the number of samples. To go back to the video analogy, sampling rate is like the frame rate of the video. Samples per chunk then, that's how many audio samples are in one chunk, and like I said, chunks are required because there are so many samples in 1 second. And to refer to this chart here, make that maybe a little easier, 1 second of audio is going to be 44,100 samples. And that number sounds kind of random, it's standard basically. Most things that are recorded, unless there's a reason not to, are done so at 44.1 kilohertz, which means that there are 44,100 samples in 1 second. So that second can be divided further into chunks. Each one of those chunks can be really whatever duration, but for the rest of the project, when I refer to a chunk, I'm talking about 0.15 seconds of audio. I determined that that was the most effective way. Okay? So to summarize here, audio is going to be recorded continuously. And every second, we're going to have a set of chunks being recorded. And in each of those chunks is some number of samples. Also, you can ask questions anytime during this if you want clarification or something. So, the first objective is to discern pitch from raw audio. And the way that that's done is using a transformation called discrete Fourier transform. And that's a transformation that separates complex frequencies into their components. When a computer does it, it's not called DFT, it's called FFT, but I have an example here to explain that. So sound, like I said earlier, is vibrations, and every vibration is a frequency. And the frequency of a given vibration is the same as its pitch. So a C note is a different frequency than a D note, which is a different frequency than an A, et cetera, et cetera. So I played a 655 hertz sine wave in my basement. And this is what it looks like. It's this wave. You can see it goes up and down at a certain frequency. When you apply DFT or FFT to that, I get a graph that looks like this. So each of these lines shows the frequencies present in this wave. And so this top one here, this tallest orange one, is the peak frequency, which is at 655 hertz, which is expected because that's the wave that I played into the microphone. But you'll also notice that there are some smaller ones down here, the other beats. And the reason for that is, like I said, I played it in my basement, which means there's background noise, there are imperfections in the microphone and the speaker. So this wave isn't a pure 655 hertz wave, it's actually a combination of multiple frequencies. And you can see that, probably too far away actually, but there are some jagged edges here, it's not perfectly smooth. And that's because this is the sum of a bunch of different frequencies. And when I apply FFT, that's how you can see what exactly those frequencies are. So the logic behind the program is that for any note being played, the peak frequency, the one that's the tallest in this graph, is the note that's being played. So I just said a billion times that pitch is frequency, which is true. But for the rest of it, there are other ways to represent pitch. One of them is by something called the MIDI number. And a MIDI number is just a whole number value that corresponds to a specific note. So whereas a C note might be something like 636.82 hertz, and then a D might be 854 or something like that, MIDI numbers simplify that by saying C is 64, D is 65. So that way, things that are one semitone apart are one MIDI number apart. And also, that's the way pitch is defined in Magenta software. So I have to convert between frequencies and MIDI numbers using this elegant formula. So I use FFT to analyze the peak frequency of the chunk. I put that frequency in here and get a MIDI number, and that's the pitch of that given chunk, you assume. So it was there that I got to my first milestone, which is being able to continuously apply FFT to a chunk of audio. So this output is from the early version of the program, and each one of these chunks has 3 lines in it. You really only need to pay attention to the first 2. Each one of these shows, 1, the peak frequency from 0.15 seconds of audio, and then the MIDI number from that, of that frequency. So if I ran this program and played anything into it, it would be able to detect the peak frequency and then the MIDI number for that section of audio. So going back to the program requirements, where are we after that? It is 1/2 through the first one. Because the first one is to discern notes from sound waves. And right now we're using a pitch for chunks. Remember, a note is defined as a pitch with a definitive start time and end time. And notes, which means notes usually stretch across multiple chunks. You've definitely heard songs with notes that last longer than 0.15 seconds. So here's where we're at now. If we have a timeline for some melody, I can detect the pitch, but I don't know what the notes are. So the next goal is to figure out where the notes started and ended. So this is a chart that shows the output from that version of the program. On the top here we have the MIDI numbers. Next 2 rows are the note equivalents of those MIDI numbers. Then we have the timeline, and the last row is important because this is what was actually played. This is what the first row should show in theory. So what's the most basic way to achieve, to determine where the notes are from something like this? It's just to say that sets of consecutive chunks with the same exact MIDI number are going to be 1 note. For example, we have 2 66s in a row here, so we can say that might be 1 note. 2 64s here, that can be 1 note, because the notes around are different. Now that works for these 3 sections, because those happen to be exactly the same as what was played, which is the goal. Like I said, there are imperfections in the playback and recording, so it's not always the case. But look at the first 4 sections here. This should all be 1 C sharp 4. Then it goes D sharp 3, C sharp 5, C sharp 4, D sharp 3. So if I use that logic, I won't get the output that I want. And this is what a MIDI plot looks like, by the way. On the x-axis is time in seconds, and on the y-axis is pitch. So if you imagine a piano keyboard displayed vertically this way, high to low, that's what this is showing. So objective 2 really is to accurately detect the beginning and the end of notes. And like I just said, the basic approach causes some errors sometimes because it's because of imperfections in audio, background noise, things like that. So I identified 3 errors that I found in a lot of the conversions. The first one is an incorrect octave. Something like here. You see this note is exactly 12 semitones away from the notes flanking it, and it lasts only 0.15 seconds. It's off by exactly 1 octave for 0.15 seconds. That's something that's commonly found. The second one is a note that's off by 1 semitone. It's probably difficult to see this distance, but we have what should be an unbroken block, which is interrupted by 1 section of 0.15 seconds long that is exactly 1 semitone beneath the rest. That was a common error. And then finally, we have an extreme error, which is off by both note and octave. As you can see, this note way down here, but the rest of them are up here. It's not the same note, it's not the same octave, it's very far away. It's wrong. So there are ways to process out some of those errors, and the first one is to condense every note into a smaller range. So this note would be bumped up, this note would be bumped up. They would all be condensed into the smallest possible range. That will reduce the first one, octave errors. The next is to correct for each semitone errors. It's relatively simple to say that if this note is 1 semitone away from the 2 flanking it that lasts much longer than it only lasts 0.15 seconds, it's probably an error. So I can go through a melody and push that up after observing that to correct that error. Finally, extreme errors will be sort of corrected by condensing all the notes into a smaller range. And then So again, being able to, if we can observe that this is likely an error, a computer can definitely. So those are ways to process out some of those errors. So I wrote that using the program. And I got, here's an example of before and after processing. Here's the original melody. And here, as shown in this MIDI plot and I'm about to play, is the melody interpreted before any processing of any kind. So if you can follow along maybe with the plot, it will help. So it jumps around between octaves. There's a semitone error here, extreme error here. So I process that, and I get a plot that looks like this, and sounds like this. Now, that wasn't exactly what I initially played, but it's much better than the unprocessed version. And because it's machine learning, it doesn't have to be exact. It's enough to capture the essence of the melody just so that it can be extended. So, so that's processing. And finally, rests. So a rest is when no note is played, there's no sound. And the only way right now of detecting rest is to say that within one chunk, if the amplitude or the volume of the wave isn't high enough, then I'll say it's a rest. But rests are often last less than 0.15 seconds. So I can filter out all amplitudes below a certain threshold and say that those are rests. Then I can account for even rests that are less than 0.15 seconds long. And that's what those red lines are. Those are a threshold. So anything between those red lines, or any peak that's between those three lines, will be assumed to be a rest, and then that can be inserted into the final melody. In order to determine where that threshold is, the program has to calibrate because it's dependent on the room noise and the volume of the instrument. So calibration is necessary to deal with rest, and once that's done, I can insert rest where they need to be. So back to the program requirements. Now you discern notes from sound waves. You determine the location and the length of rests. Detecting the beginning and the end of a melody is relatively simple. It's just a matter of saying how many rests in a row until the melody is over. Converting that to a note sequence format is a couple of loops, and then getting that to magenta is a couple of lines. So then we're done. We've completed all the program requirements, and I should be able to demonstrate now. So I'm going to invite Mr. Slauson up here.
This won't be great, so don't get excited. This will be, but this won't.
All right. So, like I just said, we need to calibrate first. So I'm going to press enter. We're all going to be silent, and I wait for 10 seconds as we record the room noise. So here we go. Alright, so the rest calibration is done. Now we need to do the instrument calibration, where you can play whatever you want for 10 seconds. Just make sure it lasts for the whole 10 seconds. And this is not the input melody, this is calibration. So, go. So now, everything is calibrated, and when I press enter, the microphone will start listening. And as soon as Mr. Slauson plays whatever, I don't know, it's 8 or 9 seconds of something, and then weights. The program should detect the beginning, record the duration, and then extend it. So I'll press enter. Sorry, we have to press enter twice. I forgot. All right. Microphone. Sound settings here. Alright, well, I do have a video. This is a little piece of the same thing. It's just a muted microphone. Well, you saw a calibration, like, so you can see that here. So here's I played something, I played the interpretation of that, and then the extension of that is Magenta software. So, as required for any engineering project, we could test how well I did. And the way I did that, like, there are many things I could have tested, but I decided to go with how accurate is this program at converting melodies that I played. And to quantify the similarity between two MIDI plots somehow, something like this. When I look at these two MIDI plots, there are a few important things to notice. Those things are, one, these notes never overlap each other. There's only ever one note playing at a time. Two, the notes are represented as numbers, MIDI numbers, all whole numbers. And finally, the actual melodies and the converted melodies are expected to be roughly equal length, okay, give or take a few seconds. And why are those things important? It's because those things, if all those are true, it means that all the melodies that I'm dealing with here can be represented as functions, mathematical functions. And the way to quantify the difference, the average difference between two mathematical functions is with calculus. So here's the formula I used to determine what that difference was, where mu is the average difference between the target melody and a converted melody. I don't want to model out equals too much, but I used this formula to find the average difference. So I wrote a program that did that, and I got these results. Now, these are only 5 melodies. You'll notice I intended to test 20 melodies 5 times each, which is apparently very ambitious because I left gave up on the 5th one, and then it took 12 hours to start the 6th. So, so we have four data points here for the trial, and I got an average result of 3.95, which means that the conversion is roughly 4 semitones off on average from the actual melody, as long as they're both defined. Roughly 4 semitones off from the average melody. In the previous slide, I kind of just chose a number. I said 3 would be successful. So technically, that's not successful according to the benchmark that I set. But I had to improve testing somehow. Those are the results of testing. And then, yeah, summary questions. These are links to all the involved programs. And yeah, I'm ready for questions.
Did you attempt to figure out the key of the melody?
Yeah, so the actual machine learning part, I think, is taking care of that for me. I didn't write any of the machine learning, that's all Google data scientists.
Gotcha.
So it's based on, well, actually, okay, so the model that's used isn't only based on what I am, but it's also based on an incredible amount of data just about music and songs in general. So if I play something in a specific key, then the model will kind of call on its knowledge of music and know that to extend something, it will likely be in the same key. And so that's how that's dealt with. Okay.
If you played the exact same melody into it, would it have the same output?
It would not, because the cool thing about machine learning is not even the people who design the program to know exactly what it's doing, it's right. So you likely won't get the same output twice in a row. It's interesting. Yes?
How would you do a melody and a harmony?
What?
How would you do a melody and a harmony?
So, a melody and a harmony would probably have to be dealt with, first of all, by a different conversion program. Because mine right now is only equipped to deal with one note at a time. In fact, if I played a single chord in the melody, then it wouldn't work. Because it's assuming that only the peak frequency is the note that I want. So to deal with a melody and a harmony would mean dealing with multiple notes at the same time and having to resolve that from just audio, which I think is very difficult because, like I demonstrated earlier, when I used the audio to MIDI converter on even my single note melody, it wasn't very accurate. So I think that would be a much, much more difficult challenge.
Thank you. Nice job, everybody. If the students would set up their posters and the projects, just pick a place around the lab, and then if you want to take a look at what they've got, we'll do that for half an hour-ish, and then everybody wants to go home. Okay? We'll bring stuff up to the lab, all right? Thank you all for coming. I really appreciate everybody and the experts that came and watched on YouTube.
Thank you for having me. Appreciate it.
You're welcome.
Thank you. Good job.
Yeah, everybody is roasted to death all around the school, and then they come up to my lab, the library and my lab. We're one of the, I'm involved in our master teacher program. I love when you're from schools that got to this point. We got a marching parade where everybody was here.
Oh, okay.
Or more than a marching parade where everybody was here. Yeah.
Really, really great. See how much they're involved and excited. Usually I get the problem. Yeah, I'm excited. Really good.
Yeah.
Great to be in the middle of it.
Right, yeah.
Yeah. know the time is going. I'm surprised by nice.
No, but I tried to get it to see if I could making a bunch of music here actually worked out.
Yes, you're also staying busy. What type of busy?
My oldest one is an elementary school music teacher, so she was trying to teach the little babies music during this COVID, and it was excruciating. She did a great job. I was kind of surprised how I think she got out of it. Now she got doing it. Not every single district. Twice expensive to have research.
Yeah. I'm just trying to
Yeah, it's been a while. I see you. Nice job out there, man. Yeah.
I think the last time I sang my SDA soccer.
Yeah, remember. I wasn't recognize you 2 nights ago. Last night, right? My goodness. I think they 3 years and they should have, you know, so you had it I
just wanted to get my girlfriend to
I would kind of shave down like a little slot, and then I would have like this fun and then kind of like communications that like snap.
That's a great fit. Yeah. Well, that's the key to success, right? Find something that you like and that you're good at. And if they both did the same, guess what? You're not working, you're having fun every day. You know? So
When you're going to have the always
Oh, really? I was just trying to find out.
You okay? You realize
well, that was a pretty good one because you know institutional ones. Mr. Campbell. Scrolling through. Nice job.
That's why I said that I had the years because I didn't want to pay all the way.
you were on my side. Yeah.
We were later in the day, that was why.
Yeah.
That helped.
Yeah, that's the big one. The main issue was solving binding issues, so I had some different types. I was trying to find all the ways I can solve it. That's why I like
Just sitting, staring at a computer.
There's all sorts of things out there. So here's so we've got a couple of different ones.
What's the largest 3D printer?
Well, it's kind accepted, but we 3D printed an entire cross. But it was done easy.
I see,
By figuring out the diagonals and everything else, you can figure out where it lands.
Yeah. Everybody knows it.
Of math. I heard that. Well, it was more of a juggling act of trying to get kids that were here, kids that were not here part-time, not here all the time. And it actually got a whole lot easier when everybody was either not here or here. That's seriously, because they're all not here and doing it. You can at least, you got the same audience. Well, there's a lot of videos out there. The issue with AE classes, everybody will do something different. So I'm not going to do a lesson on, committee controls that doesn't apply to anything else. I'm contemplating this project and CNC plasma cutter or something like that. Something different here. Build the CNC. Fire and computer control. How's it been for Mom and me?
And your voice is